Hi, this is Alex Georgescu, and welcome to my talk on Introduction to Correlated Electron Materials. So the goal of this talk is to introduce a variety of common topics, including, just basic intuition, a variety of lattice symmetry breaking modes and their interplay with the electronic behavior, applications, Mott transition, spin frustration, and the target audience is researchers and interested students. So I've actually use these slides to kind of help introduce students and other scientists to the field. There are many references here. Some, of course, are my own, and I should mention you can add more to the comments. I'll add some to the description as well. And one key issue I won't include here is actually Mott versus charge transfer behavior. Even though this is very important, I'll have another video for that. So how can we think of correlated electron materials in a nutshell? So you can think of an atom, usually a transition metal atom. So one of these atoms over here, and you can also think of rare metal ions, but I won't discuss here rare earth metals. I'll just focus on transition metal compounds. And you can think of a specific ordered electron configuration in the d orbitals. So in this atom, the d shell can hold up to 10 electrons, but here it has 5. So as a result, the spins align and you have a magnetic moment on the atom. Partial filling is needed for this type of ordered state. So if you'd have no spins in the d shell, no electrons in the d shell, then you would just have no magnetic order. If you'd have a fully filled d orbital shell, again, you would have no magnetic order, right? So, okay, if we put this transition metal atom in a material where it then talks to other materials, you might have long range order. So this is an interplay of local, so the local spin, and long range physics, so the spins aligning. So here I'm showing one example of a correlated electron material behavior, which is ferromagnetism. So the way I like to think of correlated electron materials physics is as emergent phenomena from localized states. And I should mention these localized states can be quite diverse. So they can be, d orbitals in transition metal ions, they can be f orbitals in rare earth ions, or they can be flat bands, so extended states across multiple atoms, for example, in things like bilayer graphene or Moire lattices more generally, or Kagome materials and other lattices that support flat bands. But here I will focus on d orbitals in transition metal ions. And it's worth mentioning this is a very nice review paper on kind of where the field is and where it's going. So some example applications before I go into a bit more detail. Magnetism is a quantum property in materials of correlated electron property, in particular in this usual like ferromagnet. Unconventional or high temperature superconductivity, again, is a result of correlated electron physics, as well as many metal insulator transitions, so a material that transitions from a metallic to an insulating phase. And there can be other phenomena as well as combinations of the above. Correlated materials are important in day-to-day life. So for example, giant magnetoresistance, that is basically a resistivity shift as a result of an applied magnetic field. So this reader here can tell changes in magnetic field as the disk rotates, is an important phenomenon used in hard drive disk readers. So this led to Nobel Prize in 2007, and again, standard part of hard drive readers. There are possible future applications of this type of material, like smart windows that store energy or get darker as it gets sunnier outside or brighter. So this can also help prevent a room from getting too hot, as well as a variety of other applications, such as neuron mimicking computer architecture, most likely for machine learning applications. possible phenomena are also spin liquids. Spin liquid hasn't fully been confirmed yet, but a spin liquid would be quite useful for quantum computing, for example. And they might also be used for things like dark matter detection or high energy particle detectors, as described in this paper. So again, back to this idea of emergent phenomena from localized states. You can have different connectivity between the transition metal sites, as I'm showing here, a triangular lattice versus a square lattice. And you can also, and many other types of lattices, and the local ionic environment matters as well. So the ions here can affect the physics on the transition metal site. So these ions can be oxygen, sulfur, and other types of atoms. Okay, if we take copper in a vacuum, you have its d orbitals here are degenerate. If you put it in a cubic environment, as here, you will have a splitting of the degeneracy into EG orbitals and T2G orbitals. If you pull on this oxygen, you will have an orbital splitting. So, you'll have an additional order. If you have 9 electrons in the copper D shell, you will fill these orbitals here, and you will be left with this one electronically active orbital, while all these other ones are filled. So then if you think of the coppers in a high temperature superconductor as being in this 2D plane, many models basically just treat this as, one electron per orbital in this 2D plane where they talk to each other, while ignoring all the other orbitals here. So this led to a question, which is, can we design nickel-based superconductors in a similar way? So the ingredients we need would be the same d orbital splitting and 9 electrons. And this was proposed over 20 years ago. So in this paper, and it was actually synthesized quite recently in Harold Huang's group. And, I had worked on some theoretical work on superlattices, but this was a completely different direction than what we were looking at and what many people were looking at. And here the idea is just remove the apical oxygens altogether. So this leads to exactly this type of physics and to high temperature superconductivity in a nickelette. So in conclusion, this led to a predictive theory of electron lattice interaction will lead to new materials. So it's important to understand the way the lattice interacts with the electronic behavior if we want to design new materials. So there's a zoo of lattice distortions, and I'm going to show here a few for octahedra. So if we have something like this with the transition metal site in the middle and these anions around, you can have a Jahn-Teller distortion, break the symmetry in this particular way. And I should mention that Jahn-Teller distortions in general can be important for a variety of applications. So in this article, they're shown as key to battery materials. And Jahn-Teller distortions don't only have to be in this type of structure. You can have trigonal distortions. So corner and edge connected octahedra are the ones that display this type of distortion the most. And this is some recent work I've done in this direction on dihalides and trihalides, which are edge connected, made out of edge connected octahedra. And there are also longer range distortions, such as octahedral rotations, for example, which lead to this bond bending. And as a result, there is less electron hopping between the transition metal sites. Other distortions include breathing distortions. So if you think of each of these sites having one electron, you can have something like an octahedron growing and size in the other one shrinking, and the electrons moving to accommodate this behavior. And of course, there's a complicated interplay of electronic and lattice physics here. And again, this is a work where I believe we clarified this. Okay, so again, there's a zoo of lattices, and they're distortions, and I went through a few for distortions for this octahedral type material. Okay, so these minor lattice changes can have a pretty important impact, not just on the electronics, but also on the structure of the material. So for example, if you have VO2, which undergoes a structural transition through its metal insulator transition, the material will actually crack. So it's important to avoid this when, when designing materials or designing devices that use these materials. Okay, so again, you can see the cracks here in VO2. Mott physics is one of the most discussed aspects in correlated electron physics. So if you have, for example, a 1D chain of atoms, you can think of this particular model that has 1 electron per orbital per atom. And in a purely band theory picture, you have this interatomic hopping T, which leads to this half-filled band. So this should just be a simple metal. Now, as you move the atoms further away, you change this hopping to a smaller one, calling it here T prime, and you narrow the band. But for large interatomic distances, we know that this material has to become an insulator. You can't just hop if the materials are very far away. And then one question is what leads to this metal insulator transition? One possibility is a piles distortion. So some atoms get closer to each other, as you can see here, and they form these dimer pairs. And one way to think of this is that the orbitals actually form these pairs that are then bonding and anti-bonding extended orbitals on this dimer. And this is basically what leads to a band gap opening and the material becoming insulating. It's often unclear what drives the transition when you have a coupled lattice and electronic symmetry breaking mode, whether it's electronic or ionic lattice driven. And this leads to important questions, as you know, an electronic only transition would be faster and more efficient. And I think one way to think of this type of transition is by quantifying through an energy functional the effects of the structural distortion and the electronic disproportionation separately. So here I'm giving an example of a particular functional for some materials, but you can have this type of functional for a wide variety of materials, provided you do this correctly. So, in this paper, we do this for a variety of materials, but I won't go into any details here. Okay, so we can have this piles distortion open a gap, or you can have magnetism as well. So for example, you can have, spin up, spin down, alternating. And again, you can think of this as an even number of electrons per unit cell. So this is now the unit cell. And this gap is filled, and this band is filled, and this one is empty. But one question is whether symmetry breaking is necessary to actually reach an insulating state. And the answer, intuitively is no, because at some point it just becomes too expensive for the electrons to hop. So how do we think of that? Well, one way to think of that is the fact that there will be a Coulomb repulsion, usually called U or Hubbard U, that prevents two electrons from occupying the same orbital, right? So for a large U over T, you have a Mott insulator. So the electrons are localized, and even though there is a finite T, and in principle, it should have this half-filled band, you do have an insulator. And this is why we need things like what are often called computational quantum many-body methods. So these are dynamical mean field theory, Gutzwiller methods, boson methods. And one of the questions is, which mechanism is actually the real one in many materials, whether it's the Mott behavior, whether it's magnetic order, whether it's a lattice distortion. And the reality is that often you have some combination of two or three. You might have some lattice distortion. You might have magnetic order as well. You might have Mott insulating behavior. So then it all just becomes, it becomes very material dependent. And it's quite hard to disentangle these three types of behaviors. Okay, but the thing is, we always have an electron repulsion, even in metals. So what if U is non-zero, but we don't have an insulating material? So one way to think of this, which comes, from the Hubbard model and, various boson models and Gutzwiller approximation, is to just think of renormalizing the hopping. So this Hubbard U preventing hopping leads to a lower effective hopping. So this leads to this narrower band. So this mainly affects the bands around the Fermi level, of course. Okay, so if you take strontium vanadate, which is a correlated metal with one electron in its vanadium D shell, the density functional theory here in blue gives you much broader bands than what you get in experiment, which are the, you can see here, the ARPAS spectra. You can also see Hubbard bands, but I won't go into detail on that. And again, the basic explanation here is that density functional theory, which is a band theory, doesn't take into account this renormalization of the bands from the Hubbard U. And I should mention that the way I've kind of learned about these things was while developing the subsidiary boson method, which is now in this open code, which works in MATLAB, and it's quite easy to use, at least as a starting point, as opposed to things like dynamical mean field theory. And we also have some comparisons there, between, our subsidiary bosons and DFT experiment and dynamical mean field theory here, which is the most accurate of the methods available. Okay, so again, we can think about these different models. So for example, copper-based superconductors, which are basically this 2D, you can think of the model describing them as these 2D planes of material that have one electron per orbital per site, and most often they are doped, either electron or hole doped. So again, from before, these models that we're looking at, they come from the fact that you have a very strong Young-Teller effect, which leads to this picture of one electron per site rather than 9 electrons per site, as you would imagine, or approximately 9, as again, there is usually some doping. And another topic I wanted to mention here is that of spin liquids. So spin frustration is key to the discovery of spin liquids and to their behavior. So, the classic example is if you have these two atoms and they each have one electron in this one orbital and they're antiferromagnetically coupled, right? So this one electron wants to be the opposite spin from this one. If you add a third site in this triangle, well, this one won't know which way to orient. So this is basically called spin frustration. And, I can't explain all of these things here in one video, but the thing I should mention is spin frustration is key for possible spin liquid behavior. And this is the main concept. And spin liquids, again, if you want to learn in more detail about them, this review article is really great, and it's basically how I learned quite a bit of this. So one key thing to remember about this type of material is that if we want to have a spin liquid or just interesting magnetism, you generally want to be close to a Mott transition, as you want the spins to be able to talk to each other, so they shouldn't really be isolated, but you also want them to be localized enough that this idea of a local spin is really meaningful. And when people think about, spin frustration and spin frustration leading to spin liquids, they usually think of lattices like the triangular lattice, for example, which leads, if you were to have a spin liquid, you would be able to think of the spins as communicating from one part to a very remote part of the lattice through long range entanglement. And if you were to dope a spin liquid, in principle at least, you should have a superconductor. And probably the most discussed lattices that lead to spin liquids, or should lead to spin liquids, as none has yet been discovered, are the triangular lattice, as well as the Kagome lattice, and possibly the hexagonal lattice. And of course, various Moire lattices, but I won't go into that here. So just to recap, correlated electron physics is basically novel emergent phenomena from localized states in a solid. Local physics, chemistry, and structure are all key to materials understanding and prediction, and there have been quite successful predictions of interesting new materials. There is always an interplay and competition of multiple phenomena, whether it's the ionic lattice, electron behavior, Mott behavior, magnetism, and so on. And there will be a variety of papers and resources in the description, as well as in the comments, and please feel free to add some more. So thank you for watching, and again, additional info in the description. Thanks.